Hello again, my awesome algebra students. Today I would like you to have your book out and opened up to page 147 so we can start using some patterns to help us write equations. So we've got this table on page 147 and it's got x and y are my two quantities and they're related somehow, but we want to know what that relationship is and try to figure out how they're getting from x to y, what's happening here in this pattern. You don't necessarily have to write this as an equation, you can just say it in words. And if you're stuck, you can certainly be talking to somebody near you, but if you're stuck, I think that the one that helps me the most is looking at the 7 and 48. Oh, I need my pen on. The 48 helps me. 48 is really close to a nice number that I could use for 7. Same thing with 24, really close to a nice number that works with 20 or with the 5. 3, same thing here. What we want to be able to see in this pattern is that my y values are 1 less than what the x is after it gets squared. So if I would take 7 and square it, I would get 49 and subtract 1, 48. Take 5 and square it, and I get 25, subtract 1, 24. 3 squared is 9, subtract 1 is 8. 1 squared is 1, subtract 1 is 0. So you could just write that out in words. You could also say that y equals x squared minus 1. Now, you probably didn't think about graphing to be able to figure out this pattern, but if you had tried to graph it to just see, is this a linear? Does it make it a straight line? It is definitely not a linear graph. We will be graphing stuff like this later in the year, but this is what we call part of a quadratic graph, and it's because it's curving like that. All right. Still on page 147, we've got two graphs on this page, and we've got two graphs up at the top of the next page. And this says something about 400 because all four of these tables have something to do with the number 400. So for table A, anyone that's in track is probably going to have a little bit of an advantage on this. It says the number of laps would be the x value, and then the number of meters that were run, that would be the y value. So when they run 0 laps, 0 meters. That makes sense, right? They didn't even start running yet. They don't have any meters in there at all. They run 1 full lap, they've got 400 meters. Oh, 2.5 laps, and they've got 1,000 meters. 6 laps, they've got 2,400. 9 laps, they've got 3,600. What's happening here is that every lap that they run is actually adding on another 400 meters, right? The distance run is 400 times as much as the number of laps, right? If I would multiply by 400, here the 0 doesn't really help me a whole lot to see that, but multiply by 400, yep, that would make sense. This might be a little tougher to do in your head, but 2.5 times 400 is 1,000. 6 times 400, if you just think about 6 times 4, you get 24, add the 2 zeros. Same thing here, multiply by 4, add the 2 zeros, 3,600. So here we're multiplying by 400 to get the distance. Okay, table B is a different kind of situation, and we have to make sure that we're always reading all the information that they give us. But we've got the number of meters from home and the meters from school. So when you are 0 meters from home, that means you haven't left home yet, right? This is when you are at home. You are 400 meters from school. And then if you start walking toward the school, so you get a little farther away from your house, but you're a little closer to the school. And keep walking. You're farther from the house, closer to school. Farther from the house, closer to school. Here you are almost at school, right? You're only 4 meters away from school, but you're 396 meters from home. Can you see what's happening with those numbers? How are we going to use 400 in this pattern? Or can you tell me what's important about 400 in this pattern? I hope that you can see here that your house, your home must be 400 meters away from school, right? There's 400 meters between home and school. Right? There's different ways that we can write that as an equation. We'll be doing that in just a minute. All right, take a look at table C. We've got an electricity bill for, this must be different months maybe, or maybe different, maybe it's different apartments in the same building or something. But we've got the electricity bill and then the total expenses. So again, remember this is something about 400. What's happening here? What's the relationship between these two things to go from the electricity bill to the total expenses? Well, this is 85 to 485. 124 to 524. 309 to 709. Right? Isn't it just saying that the total expenses are always going to be $400 more than the electricity bill? Right? So add 400, well, it's a bad 400 there, to electricity bill. That does say bill, sorry about that, to get total. And for table D, you get a monthly salary. So some people would get paid a salary, which means that they would know exactly how much to expect every single month. And then some people get all of that money deposited right into the bank. By the way, that's what deposit means, it means that your money is going into the bank. And some people get that money as an actual check and they keep some money out and they only put some of the money into the bank. So let's figure out what's happening here in this table. The monthly salary for the first person was $872 and they deposited $472. Second person was $998 and they deposited $598. Heroes $1,015, they deposited $615, or $2,110, they deposited $1,710. So every month, or for these different people, I guess, they are depositing $400 less than their monthly payment. Now, that could be, if it's exactly 400 every time, that could be, sometimes people have like an automatic amount taken out to go into savings, or it's going for some kind of a payment on something, but the amount that's being deposited is $400 less than the monthly salary. So what we want to do is take a look at what we figured out for those four tables and figure which one of these equations matches up with each one of them. So starting with the first one, I'm going to say table A is probably the easiest one to see because this is the only one that had anything to do with multiplying. So if I look at these four options as equations, the only one that has multiplying is equation 4, right? That one is going to be 400 meters for every lap gave us our total distance, right? That's table A. All right. For table B, it was 400 meters between home and school. Now, I didn't write this, I purposely didn't write this so that it would be easy to see it as an equation. But I know that the total distance And it's probably easiest to see it, I think, with these two. The total distance is always going to be 400 meters, right? The distance from home, the distance from school, because there's 400 meters between the two. If you just measure the distance that you are from home and the distance that you are from school, that total should be 400 meters each time. So looking at these three equations that are left, I want to know which one says that if I add up the distance from home and the distance from school, I'm going to get 400 as a total. That one has to be equation 3. For table C and table D, table C says that we were adding $400 to the electricity bill to get the total. Now keep in mind where we've got our X's and Y's. So I've got my X is my electricity bill, and I'm going to add $400 to get to that to get my total. So for equation 1, that one says my that was the electricity bill was X, add 400, and that's going to give me my total. So that's going to be C. Well, I only have one left, so it makes sense that I know which one it's going to be, but let's just make sure that this makes sense here. To go from the monthly salary to the amount that's deposited, I'm depositing $400 less. That means I'm subtracting, so it should be X minus 400 to get me my total amount that's deposited. So that should be D. And that matching stuff was all on page 148. Okay. So we're going to skip this because I'm not there with you to take the time to go over those. So we're going to move on to the top of page 149. We've got this relationship between the base length and the height of some parallelograms. Hopefully you remember what a parallelogram looks like. A parallelogram is like a rectangle that kind of gets squished to the side a little bit, right? So it could be something kind of like that's a really bad drawing for you, I'm sorry. But there's a parallelogram. I've got the base and the height for a bunch of different parallelograms here. But the area formula for the area of a parallelogram is base times height. That's kind of a big hint that I'm giving you here. I also want to mention that as the base length is increasing, as these numbers are increasing, these numbers are decreasing over here for the height, right? So that might be something that you are looking at as a pattern. It doesn't necessarily follow a linear pattern though, so we can't just say as one thing is adding, another thing is subtracting. This one, I think we have to take a look at this in terms of area. If I would multiply the base times the height, 1 times 48, well, that's 48. 2 times 24, well, it's 48. 3 times 16 is 48. 4 times 12, 6 times 8. All of these different numbers here give me the same area. So that's the relationship between the base length and the height. The area of each parallelogram that's R, is 48. Now this is an area and these are measured in inches, so this should be square inches. Okay, visitors to a carnival are invited to guess the number of beans in a jar. The person who guesses the correct number wins $300. But if multiple people guess correctly, then the prize will be divided evenly among them. What's the relationship between the number of people who guess correctly and the amount of money that each person will receive? Well, if only one person guessed it right, they would get all $300. If 2 people guess it right, I would have to take 300 and divide it by 2 people. Or if 3 people get it right, they have to do 300 divided by 3. So what we're going to be doing for each one of these is we're going to have 300 divided by the number of winners. right? So as an equation, we could say the amount that each person wins could be 300 divided by the number of winners. And this is the amount that they're going to win, or the amount won, we'll see. All right, I didn't write an equation on that first one, but we certainly could go back and take a look at that one. The area for each of these is going to be base times height. And because all of these were 48, I could even change, instead of having an A right here, I could say that this is going to be 48 equals base times height. Okay, number 3. A half-gallon jug of milk can fill 8 cups, while 32 fluid ounces of milk can fill 4 cups. What's the relationship between the number of gallons and the number of ounces? If you get stuck, try creating a table. So this one is a little bit tricky. Now, I would say that what's important here is that they give me 2 different things that both have cups. This had cups and this had cups. I know I'm trying to get gallons and ounces together, but let's write down what we know. So we know that a half gallon is 8 cups. And I know that 32 fluid ounces of milk, well, let me do one more step here. In case you aren't aware, each cup has 8 ounces. So if I would take 8 cups times 8 ounces in a cup, that's going to be 64 ounces. OZ is the abbreviation for ounces. If I had the 32 fluid ounces in 4 cups, let's go right here, 4 cups and 32 fluid ounces. Oh my goodness, I can't write. 32 ounces. I don't necessarily care about the fact that that's half as much, which would be a quarter of a gallon or a quart of milk, but I can see that everything got cut in half. If I want to know for 1 full gallon, well, this was only a half a gallon, right? If I wanted 1 full gallon, it'd be twice as much as this one, which would be 16 cups. And it would be twice as much as this, which would be 128 ounces. And I know I should be writing fluid ounces for each of these, but to get that equation then for all of these, or to figure out how to write that out, to get the number of gallons into ounces, I would have to multiply the gallons by 128. Right? Let me just write that in words actually. Multiply gallons by 128 to get ounces. Because now on page 100, oh, you don't have this matching part, do you? But I do. For these, I kind of wrote out at least parts of these. This one is obviously our parallelogram one. Things that remain constant and things that vary is what's asking here. In this first one, the thing that remained constant was the 48. Every single time we had the same area. That stayed constant. Numbers are constants. We even call them that. The things that varied in that first one were the base and the height. That changed every single time. We had different options there. For our winnings at the carnival, that was, I wrote the equation kind of like this one right here, right? But they've got another option there. The thing that remained the same was they were $300. That was the prize. But the number of people that won it and the amount of money that they would win, that would vary. That's why you've got variables there. And for the last one, I didn't write that equation out, but the number of fluid ounces would be 128 times the number of gallons. The 128 is a constant. The number of fluid ounces, the number of gallons, we can change those. That's why those are variables. Okay. This is not in your book, and I know that this video is already going kind of long, so I'm going to try to hurry. If I gave you something like this situation right here, a student starts their new semester with $30 in their lunch account, and each lunch costs $1.75. What's the relationship between the number of school lunches purchased and the dollar amount left in their account? So if they started for this one with that $30, I would have the amount in their account would be $30, and I'm going to subtract $1.75, but I don't just subtract $1.75 one time. I subtract it every single time they get a lunch, so however many times they get a lunch. So I'm going to use the letter N there, that variable, to show that that's how often it's happening. And in the second example, we've got a chef that's pouring oil from a large jug into equal-sized bottles. Depending on how big the bottles are, as long as they're all equal size, it's going to change how many bottles it takes. So for the first one, it only took 3 bottles because he was putting 24 ounces in each bottle. But it would take 4 bottles if it was 18 ounces in a bottle, 6 bottles if it was 12 ounces in a bottle, 8 bottles if it was 9 ounces in a bottle. It might be kind of hard to see this pattern at first, but what's really happening is 3 bottles times 24 ounces in each one, that's 72 ounces. And if I would do 4 times 18, also 72. 6 times 12 is 72. 8 times 9 is 72. So to figure out how to write this part, I would have to say, well, however many ounces I had, which was the 72, I would have to divide it by however many bottles they were filling up, and that would tell me the number of ounces that would go into each bottle. All right. This is in your book. This is on page 150. If we know the relationship between two quantities, it might be really easy to see what that equation should be. So for instance, the perimeter of a square. The perimeter is 4 times the side length. Or we can rearrange it sometimes and have, for instance, the side could be over here by itself and have the perimeter divided by 4 would give me a side length. This is the one that we need to look at though. Might take a little bit of work to figure out. It says a plane that's leaving New Orleans and heading to San Diego. So New Orleans, think about where that is. San Diego's in California. And this is kind of like the between your house and the school kind of problem. It's always the same distance between New Orleans and San Diego. They don't just magically get closer, but as this plane is flying, the longer it flies, the farther it gets away from New Orleans and the closer it gets to San Diego. But if I add these two together, I get 1,600. 1,600 here, 1,600 here. So you might have to do a little bit of subtraction for me, but if I did 1,600 minus 1,020, this should be 580. These also add up to be 1,600. Now, if they're 1,450 miles away from New Orleans, they have gone a really long way. They are only 150 miles away from San Diego. All right. This is just more stuff that's in your book. Again, because I'm going really long on this video, I'm going to kind of cut this a little shorter. But this is just different ways to look at those exact same 3 things that we just did for our San Diego and New Orleans. If I add the 2 together, it gives me 1,600. If I said 1,600 minus the distance from New Orleans, it should tell me the distance that I still have to go to get to San Diego. Or I can flip it around, and if I would say 1,600 minus the distance from San Diego, that would tell me my distance to New Orleans. If a company decided to donate a certain amount to charity, and it'll select up to 20 different organizations, and I wanted to know how much money they were going to donate to each organization, well, if it was $50,000 and I divided it into 5 different charities, they would each get $10,000. Or if there were 10 different charities, they would only get $5,000. And if there were 20 charities, they would only get $2,500. But if I wanted to write this so that it could be used for any situation, the amount that they would receive, this should be equal to D. The dollars that they would receive would be 50,000 divided by the number of charities that they chose. All right, so today we talked about using words and equations to describe a pattern, and how to, when given a description of a situation, you should be able to represent things like diagrams or tables to make sense of a situation and then write an equation for it. Your homework today is on page 152 to 155. It's numbers 1, 2, 3, 4, 7, and 8. If you need help with anything, send me an email.